Okay, so last time we stopped by describing the consequences, so the results, the solution to the Rankine-Hugoniot conditions. So the context is that of a Newtonian ideal fluid, and in particular we focused on the result of a supersonic, of a strong shock. It goes without saying now that you know that I could speak just in terms of shocks. I don't need to say supersonic shocks because by now you know that in order for something to be called a shock, it has to be supersonic. Otherwise, it wouldn't be a shock at all. And this because, interestingly enough, in my opinion, this would violate the second law of thermodynamics. Okay, so this is just a very quick summary of what we ended up with last time. So, what about the nature of these shocks that we are talking about? Well, first of all, let's focus on the width of the spatial width of the shock. So we last time we focused on the description of the thermodynamic microscopic variables that we use to describe the status of a fluid, so pressure, temperature, density. And I said, okay, across the shock represents a kind of discontinuity. But as a matter of fact, discontinuity in physics has no real meaning. So what happens? Well, if you remember the limit of the description, of the Eulerian description, it means that essentially, in the case of a shock, across the shock, these variables change over a length scale which is comparable to the mean free path of the collisions. In the end, you have to, in order to have the fluid that undergoes some change, some macroscopic change, so it has to, of course, to go through some kind of collisions or something which alters the content of kinetic energy, linear momentum of the individual particles. So in this case, it's interesting to consider, to calculate the width of the shock, which is given by what? Well, will be given by the mean free path of the collisions if we think of a collisional shock. So collisional shock is a shock in which the individual particles change their energy and linear momentum content thanks to collisions. So in order to do that, well, let's calculate the mean free path. So what I call delta, I mean by delta, I mean the width of the shock, and lambda is the mean free path, which you know is 1 over n sigma, where n is the particle density, number density, and sigma is the cross section of the kind of collision you have in mind. This is a reminder of what we've seen in the case of radiative transfer. So this is also kappa, the opacity times the mass density. And okay, so let's see a few examples for that. Let's consider, for example, what happens in the Earth's atmosphere. Well, the particle density is now, you know very well, is of the order of Avogadro's number per cubic centimeter. So kind of 10 to 23. I don't care about coefficients, just is an order of magnitude evaluation, okay? So 10 to 23 centimeters is typically the order of magnitude in the case of atmospheres density, particle density. And sigma here, well, if you consider neutral matter, you can take just the kind of section of for example, nitrogen atom, where AB is the Bohr's radius. So the Bohr's radius in this case is more or less half angstrom. 1 angstrom is 10 to minus 10 meter or 10 to minus 8 centimeter. So if you work this out, you see that the mean free path, so the corresponding width of the shock is 10 to minus 7 centimeters. So it's really narrow. In the case of a collisional shock that happens in the Earth's atmosphere, what happens in a more astrophysical context? So when we think of typical densities we meet in when we consider astrophysical plasma, well, the big difference, and you immediately spot it, is about the number density. So the number density that you might find typical in an interstellar medium, so still within our own galaxy, but between different stars, so interstellar medium, is of the order of a few particles per cubic centimeter, or just in the surrounding of a star. So, for example, a few parsec away from a star. This is very typical. One particle per cubic centimeter. So there's 23 orders of magnitude difference. And again, here you consider the same cross-section as before, or the Thomson cross-section, depending on the whether it is neutral, completely ionized. But in any case, you can immediately see that the big difference is given by the dramatic change in the density of the denominator, which means that the corresponding width of the shock explodes, because from 10 to minus 7 centimeter, you end up with 1,000 astronomical units, or even worse if you consider if you have the Thomson cross-section instead of the hydrogen atoms area, let's say. So of the order of cosmological distance, 0.1 gigaparsec, so 10 to 8 parsec. So what does this mean? Well, if you consider that particles just interact through collisions, it means that the shock is incredibly large. So now the question which rises is isn't there any other mechanisms through which particle can change over a much shorter length scale their linear momentum energy? Well, you know very well that if the plasma is made of charged particles, and if there is any magnetic field, for example, surely this is able to change their linear momentum. And so let's consider in particular, for example, what happens in the surroundings of a supernova. A supernova, as I probably already told you when I was talking about the Crab Nebula, the typical velocity you have, expansion velocities of the order of 10 to 4 kilometers per second. So here it is. And why I'm considering velocity, I didn't tell you yet, but because of course the typical width, so the typical length scale over which the particle will change significantly, for example, direction of motion, is comparable to the Larmor radius. If you are in the presence of a magnetic field, B, the charge, I just took E, the electron's charge. Let's assume that the particle has a velocity V and a mass M. Well, you know, from very basic physics, the Larmor radius, so the radius of the kind of circle that will be described by the charged particle is, I called here RL. So clearly, the width, so the length scale over which the particle will change direction is comparable, becomes comparable with the Larmor radius. So let's calculate it. So the Larmor's radius is just a matter of assuming the velocity, which I was just telling you. So in the case of a supernova, 10 to 4 kilometers per second. And B, the typical magnetic field that you have is very small, of the order of microgauss again. So if you work out these things, assuming the velocity, as I said, of this kind and the magnetic field of this kind, you see that the corresponding Larmor's radius is of the order of 10 to 10 centimeter, which might sound large to you. But if you compare with the previous value, I remind you that one astronomical unit is 10 to 13 centimeter, more or less. So this is 10 to 16 centimeter, or even worse. So again, this is orders of magnitude shorter. So it means that, as a matter of fact, in typical situations in which you are coping with astrophysical plasma, essentially particles exchange energy and linear momentum over a length scale which is due to the presence of a magnetic field. These are called non-collisional or collisionless shocks. Because as a matter of fact, particle undergoes a change not because of the collisions between themselves, but because of other and typical, the example of the presence of a magnetic field. You see, even if the magnetic field is relatively small, but yet it's enough to make these mechanisms more important, dominant with respect to what we would expect from the collision between particles. And this is merely due to the fact that the number density is really small in comparison. So in this case, even if it is counterintuitive, because we are all the time led to think to the everyday experience we have about shocks. So what happens, for example, in the Earth's atmosphere, where the air density is much larger than the typical astrophysical plasma densities. But as a matter of fact, in the space, in the presence, as I said, of astrophysical plasmas, what gives you the width of the shock, so the mechanism is just collisionless. So is the action of the magnetic field which changes the content of the so you have to think, for example, in the commoving frame of the shock, you have a magnetic field. This magnetic field just is capable of just changing the directions of the motion of the particles. Of course, a magnetic field in a moving frame means that if you work out then a Lorentz transformation, you change the reference frame, you see also an electric field. So that also explains also why also not only the linear momentum but also the energy changes, because otherwise you know that the magnetic field cannot change the magnitude of the linear momentum and so the energy. And one of the consequences of the collisionless shocks at variance with what you have instead in the case of collisional shocks is the fact that the population of electrons and ions do not have necessarily the same temperature, because as a matter of fact they exchange through the magnetic field, but not the two populations are not essentially in equilibrium between themselves. So assuming the same temperature for the two populations is sometimes wrong. It's not granted at all. And this is also worth keeping in mind. Now, we saw the physics of shocks. In particular, we saw how the macroscopic variables that describe the status of a fluid change in a discontinuous way across the shock, which, as I said, okay, as a matter of fact, it changes. These variables change over a length scale which is comparable with the mean free path, whatever the shock is. But from a macroscopic point of view, so having in mind the Eulerian description, it looks like a discontinuity, which, as I said, might. There's also a sentence in Latin by Lucretius, which says that nature doesn't make jumps, doesn't make discontinuous, which this is really contradicted by the evidence of shocks. So this is one of the peculiarities of fluid dynamics, which is really interesting. But so it is plausible from a point of view, because energy, linear momentum, and mass are conserved. So as soon as you make sure that these are conserved, you do not violate any big law of physics. So it's plausible. But saying that something is plausible doesn't necessarily mean that something will happen in realistic situations. So let's see, as a matter of fact, how shocks can form. And in particular, this scheme, for example, these are plots which shows you as a function of a path, which this is just the horizontal axis x, shows you, for example, fluctuations in density. Here, this value corresponding to the horizontal value here is just a reference value, which we call ρ0. So this function shows you as density changes as a function of the path along which the wave is propagating. So you see that at some point you have a perturbation, which is just the top panel here. And here I use different color to say, to highlight the compression, because here you are above the average value. So it means that here the density is slightly larger. So you are compressing the fluid. And here on the opposite, of course, you have a slightly smaller density. So it's more, it's going through a rarefaction Okay, so this compressed is more less dense. But if you remember, in the case of, for example, of an adiabatic shock, if you remember, the velocity, the sound speed, scales with density to 1/3. So it means that at some point here, density is slightly larger. So the velocity of the sound velocity will be larger. And the sound speed is the speed at which the perturbation propagates. So if you imagine this perturbation is just moving along the X-rays, after some time, this guy will move faster than the rarefaction. So you will move from this situation to this one. And again, when these are very close, you see that you reach the point in which, over a very short length scale, the density just undergoes a kind of jump. So this is a natural way. And yes, and this kind of change in the profile of a wave in a fluid is also referred to as turnover. And you see how this naturally leads to the formation of a shock, because then in the bottom panel you clearly see that you just reached the point at which you can describe as a discontinuity. So there is a significant jump over a very small length scale, so comparable with the mean free path. So that's the typical way how shocks can form. Clearly, in the case of a perturbation, unless the perturbation is not strong enough, then it fades away, for example, due to viscosity when you consider viscous fluids. But another possibility, of course, if you have something which is moving within the fluid, and for some reasons, this object, this macroscopic object, is moving already at supersonically. And that, of course, induces the surrounding fluid to automatically move as a consequence to supersonic speed. So that's also a possible source of shocks. And that's the example I was mentioning repeatedly last time. When you have a meteorite or a space shuttle or whatever travels in the air, or just a warplane, this fighting these very, very fast planes which are used for fights, for battles, which can travel much faster than the speed of sound, and so they develop shocks. So this is another possibility. Now let's see applied all the Newtonian physics of the shocks of the Rankine-Hugoniot conditions to a given situation. So let's consider a fluid which is homogeneously distributed and at rest in some region of space. And this fluid has a constant density, which we call ρ0. And we consider this fluid as kind of cold. And I'll be more precise what I mean by cold. But cold means that the temperature and the pressure are so low that we can just consider as they were zero. Okay, so negligible pressure, negligible temperature. So very, very easy situation. Now what happens is that at some point, at a given instant that we call t0, at t0, in one point in space, in this fluid initially at rest, there is a sudden release of an amount of energy E. So you can think of any possible mechanisms capable of doing that. For example, a very powerful explosion. If you have a bomb or whatever, a bomb, you can see the effect of a bomb as just a sudden release in a very small region of space of energy, which is then transferred to the fluid, and then you would expect that a strong perturbation in the fluid just propagates. So a shock in particular. So now the goal is to try to describe the status of the fluid by exploiting what we've learned about shocks. But what we want to describe is that you take a generic point in space, so with a generic spatial coordinates at a given time. Our goal is to obtain a set of functions in particular pressure, density, temperature, and fluid velocity, at any given point as a function of space and time. So the full hydrodynamical solution, we want to know at any point in space, at any time, what's the status of the fluid. So both in terms of hydrodynamics, so velocity, and also thermodynamics, so pressure, density, temperature, whatever. Let's start from describing the most obvious thing. Well, for let's suppose that the release of the energy release is spherically symmetric. Okay, so the same amount of energy is expected to propagate to all directions. So we are in the case of a spherical symmetry. Let's call, so if you imagine this explosion, the propagation will be the propagation of the front of this explosion will be described by an expanding sphere. So you need just the radius to describe the radius of the sphere or of the shock, which I call capital RS, S stands for shock, as a function of time. Yes, presumably as time passes, this shock will expand. So an expanding sphere. So the first goal is to describe the temporal evolution of the radius of the shock. So we call RS as a function of time. Now, think for a moment. What are the variables, the physical variables, which are supposed to drive, on which the radius, the shock radius, is supposed to depend on? Well, let's review what we have. We have the energy, the total energy, capital E, of the explosion, and then surely things will depend on the density of the medium we are considering, so also rho zero. And then, of course, given that the radius of the shock changes as a function of time, if we call a generic time t, there is also. If you think for a moment, you have nothing else. And one of the peculiarity of Newtonian fluidodynamics is that if you think for a moment, you have no universal constant that sets somehow the scale. You don't have Planck constant. You don't have the gravitational constant. There is no constant, universal constant that somehow sets the scale of the phenomenon. No, nothing like that if you think for a moment. So the only things that the shock radius can depend on are these variables, these three variables. There's nothing else, because I'm not considering any other ingredient, let me say. And there is no such universal constant that could come into play. And beta here is just an adimensional constant, numerical coefficient, which I cannot know now. But you immediately see what is the goal. So my ansatz is that the dependence is like a product which each of which has its own power law index. So I call X the power law index dependent, that which expresses the dependence on energy, Y the one on density, and Z the one on time. So this is just the simple ansatz. And now you see that you have three physical quantities: energy, density, time. You have three which depend on, all of them depend on just the mass, length, time. And so you see that you can exploit a dimensional equation, and demanding that the three indices must make up something which is a length, because we, in the end, what we want to find is a length, the radius. So if you do this very simple exercise, something that you probably, this is one of the very first things you've learned in your career as a physicist. So just collect all the masses, so x plus y. Here you don't have any masses, so x plus y must be 0. What about length? Here you have 2x, and here you have minus 3y, and this has to be 1, because in the end you want length, so 1. And time, you want no time whatsoever, so minus 2x plus z. So this is just for kids, and the solution is straightforward. There's this guy here. So it means that the only way you have to end up with something which is a length is this combination of indices. So it means that you can immediately write straight away that the shock has to move this way. So really, really powerful example of dimensional calculation, because you see, you immediately nail the temporal dependence. So 2/5 time to the 2/5 temporal dependence, incredibly beautiful. And also as well as the dependence of the other variables. So you see, understanding clearly, for example, that for a fixed time and density, the more energetic the explosion and the correspondingly larger, well, e to the 1/5. So it's quite smooth dependence on energy. But again, and you see, for a given energy at a given time, the less dense the medium and the correspondingly faster will be the shock. You can just derive with respect to time, and of course, if you derive the position of the shock as a function of time, what you get is the shock velocity, Vs. Very, very simple, and indeed, the beauty here is that you also get rid of the unknown beta constant, because then if you know the shock, Rs, you see, it's just really something for kids. So this is really beautiful. Just based on this, you derive the velocity of the shock as a function of the shock radius itself and time. Really powerful. But so far, okay, we didn't solve the problem I was mentioning. It's very ambitious. We want to describe the thermodynamic quantities as a function of point in space and time, just as a consequence of the passage of the shock. But let's think of what we know from the shock, from the Rankine-Hugoniot. If you think for a moment, when we studied and we obtained through the Rankine-Hugoniot conditions, we obtained the corresponding solutions. The solution of the upstream for the upstream and for the downstream fluid as a function of the upstream fluid properties. It's something which holds true as long as we stay right very close to the shock. So very close meaning upstream, just very close before upstream the shock, and very close downstream. Here, what we want to find is something more, in the sense that if you think for a moment, just think of a point in space. Let's suppose the shock is somewhere here at some point, and let's assume that the shock is moving rightward from left to right this way. Now, at some previous time, when you consider a point here on the left, the shock must have crossed this point, but now it's already some time, so the shock has went forward, has went beyond. So, but I do expect that temperature, pressure, and density of the fluid here will still somehow be affected by the passage of the shock, even if this point is no more right, very, very close to the shock. So what we can exploit is the fluid's properties very close to the shock at some point. And this is exactly the kind of information that we know from the solutions to Rankine-Hugoniot. Just close to the shock. We know it. We know the fluid very close to the shock. So let's start from that. So let's start from the situation, from the properties of the fluid right downstream, right behind the shock. So imagine you are riding the shock. You're just right behind the shock. So where the fluid which has just been crossed by the shock, okay? We know that in that case, we can apply the Rankine-Hugoniot solutions. So in particular, if we call V2 the velocity, now the goal, mind that what we found in the previous, a couple of days ago, was referring in the shock frame. Now we want to describe, we are interested in describing the fluid in the lap frame. So we have to make a transformation back from the shock moving frame to the lap frame. So with reference to the notation I used last time, we called the prime quantities in the lab frame. So what I now call V2 is what I called last time U2 prime. But look, here is just a reminder. I just copied the solution in the case of a strong shock, because I don't know if I told you here, but we are in the case of a strong explosion, strong shock. So strong explosion will develop a strong shock. So these are ranking Hugoniot solutions in the case of a strong shock, something we already considered. So here I just copied. You see all the solution. Now U2, what is that? Well, first of all, if I call here, I call Vs the velocity of the shock, and with reference to the notation I used here last time, that's what we call U1. Okay, so Vs is the velocity of the shock in lab frame, which was at the time U1. Now, here it's just a matter of Galilean transformation, very, very simple. You are moving from the shock frame, which is moving with respect to the lab frame with Vs. So V2 is just U2 minus Vs. Here is with the sign, with the minus sign, just because of the convention that I was mentioning before last time. Here in the lab frame, the positive direction is assumed to be from left to right, which is opposite to the one we assumed in the shock frame. So instead of being U2 minus Vs, as it should be, it's just U2, it's just Vs minus U2. Just like that. Or if you want, another way to put it is just the absolute velocity, let's call it this way. If the relative velocity is the velocity relative to the shock frame, and absolute meant to be with respect to the lab frame, is just the velocity of the frame, of the moving frame, plus the relative velocity. The relative velocity has a minus sign because of the different convection, as I was mentioning, just like that. But you see, U2, what is U2? Well, U2 is the velocity of the downstream fluid in the shock frame, which is essentially the solution, one of the solutions of the ranking Hugoniot. So U2 is the velocity of the downstream fluid very close to the shock in the shock frame. But this guy is exactly what we know from the solutions. So U2 here, if you look at this equation here, you can express U2 as a function. You bring U2 on the other side and this guy on the other side. So U2 is gamma minus 1 over gamma plus 1 times U1. But U1 is Vs. So U2 is gamma minus 1 over gamma plus 1 times Vs, just like that. And so now you work out this subtraction. This is just for kids. You immediately see that this is twice over gamma plus 1 times Vs. So this is the velocity. What I call here V2 is, let's remind ourselves what we got. It's the velocity of the shocked fluid, so of the downstream fluid, in the lab frame, very close to the shock, because that's what ranking Hugoniot solutions tell us. Very close to the shock. Now the goal is to move away from the shock, still in the downstream region, but away. We want to calculate all the velocity, for example, the velocity of the fluid at any generic point, not necessarily those which are very close to the shock. But ranking Hugoniot solution tell us only about the fluid which is very close to the shock. So we have a kind of, the ranking Hugoniot solutions tell us a kind of boundary conditions about velocity, pressure, but then how can we calculate at any generic distance from the shock? We'll see in a moment. So of course you are supposed to do the very same thing for all the other macroscopic variables that we want to describe. So in particular, well, in this case, when you move from the shock frame to the lab frame, it's easier than in the case of the velocity. In the case of the velocity, you have to apply Galilean transformation. Here, nothing up whatsoever. Density are just densities in Newtonian physics. They do not change. So ρ2 is just, look at here, ρ2 is just gamma plus 1 over gamma minus 1 times ρ1, but here ρ1 is what? ρ1 in that frame is just the density of the unshocked, of the upstream fluid, but in this case, this is exactly what we call ρ0. So the density of the unperturbed fluid. So let's call it as it is, ρ0. Easy. What about pressure? Well, the pressure of the shock fluid right behind the shock is this guy here, where ρ1 is just ρ0 and u1 is the velocity of a shock. So just like that. You see, I just took this one and this is becomes this one. Very simple. I don't care about temperature now because I assume that as soon as I know pressure and density, I assume an ideal fluid, I know automatically, or I have all the means to calculate straight away temperature. So that's why it's enough for me for now to consider velocity, density, pressure. So now you see that this is the goal we want to obtain. So assuming that a generic time t, the shock has this radius here, we want, if you take a generic position, we are in a spherical symmetry situation, okay? So to specify the point in space, you just need the distance from the origin of the explosion. So r. So for any r between 0, so the point where the explosion took place, and the shock, so this is the region in which you have the fluid which has already been shocked. But presumably, so the temperature, density, pressure will be not the same as the unshocked fluid, but it will evolve sometime. It will evolve with time, depending on distance and time. So the goal is to find these three functions. So how density, pressure, velocity of the fluid change as a function of time and space. Within the fireball, if you imagine that the sphere described by the shock is a kind of fireball, it is a fireball if it is a very powerful explosion. So you want to describe the thermodynamic and fluidodynamic quantities at any point, at any time within this fireball. How can you do that? Well, you have to apply again the equations that rule the hydrodynamic of a fluid, which again is conservation of mass, energy, and linear momentum, just like that. Upon doing that, we make a consideration. We see that, as a matter of fact, because of the very same reason I was telling you before, these functions, since there is no universal constant which sets the scale, it means that if I call ρ2, as I did before when I exploited Rankine-Hugoniot solutions, ρ2 is the density of the shock fluid very close to the shock. So essentially when R equals capital RS. That's the only solution I know. Well, I can define an adimensional function, which I call capital R, and this function has to be adimensional because the density at the generic point R at the generic time t has to be a density. So, and this is already set by ρ2. And in particular, if you think when R equals the shock radius, capital RS, well, this function has to be 1, because this is the boundary condition set by Rankine-Hugoniot solutions. Because I know that when I get close to the shock, ρ has to be necessarily equal to ρ2, which is the solution of Rankine-Hugoniot solutions. So this function is an unknown function, adimensional function, but which I know has to be 1 when R is the shock radius. And but you see, how can I make a function which is adimensional and that can only depend on, again, energy, density, and space and the radius of the position of the generic point and time? Well, again, I have four variables and 3 dimensions, so there is only one combination of that. In particular, what I can define is an adimensional quantity which I call psi as the ratio between R and RS. Now, if you remember, The only way you can have a length scale depending on energy, density, and time is exactly what we exploited with the dimensional calculus, and we obtained the dependence on the shock radius. So the only way, by adding the variable r, the position of the generic point, the only way to have an undimensional variable is just the ratio between the two, because here you have no other way to end up with a length scale depending on energy, density, and time, which is Rs. So the only way to have a dimensional quantity putting into the game the space coordinate R is just the ratio between these two. So this function, this a dimensional function, capital R, is to be a function of this variable psi. And that's why, and that explains you the name of self-similar, because this immediately tells you that rho will depend on the position for any fixed time t, will depend on the position, but just in the sense of a ratio between the position that you take normalized with respect to the shock radius. So it means that for any time, for a fixed time, the density will be the same, even if you consider two different times, for example, and you work out the density when you are, for example, at 0.75 times the shock radius, so 3/4 of the radius. This ratio is the same, so the density will scale with respect to the shock density, so to the ρ2 will be the same. I'll try to clarify this with the example then of the solution. So that means that having already found the shock radius, this guy has to be something like that. Of course, density has no special meaning with respect to the other two variables. So the very same line of reasoning can be followed also when you reason about pressure and velocity. So you see here, let's focus on density again. Here I wrote it explicitly what ρ2 is. Let's get back for a moment. ρ2 yes, ρ2 is this guy here. So you see, that's the very here, ρ2. So it's the solution, it's the value of the density of the fluid in the lab frame, downstream fluid, very close to the shock. So when this function essentially is 1. And when is this 1? When psi is 1. R of, when the ratio is 1, it means that I'm right close to the shock, attached to the shock. And this has to be 1 because rho at that distance has to be this value here. So I just took the analog solutions of the Rankin-Hugoniot in the lab frame. So the pressure we just obtained from the previous slide, that the pressure close to the shock in the downstream region is this guy here. So I call a general adimensional function capital P. And again, this P is a function of psi because that's the only way it can depend on a generic position R as a ratio between R and the only variable which sets a length scale, which is the shock radius. So again, this function is similar. It's not the same as this one because there's no reason why pressure should behave qualitatively, mathematically in the same way as rho. But what I can surely state is that this function is normalized as to be 1. The boundary condition is that it has to be 1 when psi is 1. And the very same thing is here. The velocity of the shocked fluid is this guy here when you are close to the shock, still in the downstream region. So this capital V, again, will be a function, an adimensional function, which has to be 1 when for psi equal 1. So you immediately see that, yes, this is exactly what I told you. And the reason of why it is called a self-similar solution, the solution that we are gonna comment in a moment, is that because you see these three functions tell you the velocity, the pressure, and the density of the shock fluid in units or relative to the corresponding values right behind the shock. Okay, so if at some point I have this function capital P, which is 0.3, it means that at the point at which I am considering the pressure, at that point, the pressure is just 30% of the fluid pressure, of the shock fluid pressure, which is right behind the shock, close to the shock, attached to the shock. Okay, so it's a kind of scaling. The shock radius just gives you the length scale, but then the scaling with distance and time of the pressure, density, and velocity is just scaled correspondingly. So what are we supposed to do? Well, if you want to find the status of the fluid at any generic position, there's no way. You have to apply equations that we've seen in the previous classes. So conservation of mass, here it is. Conservation of linear momentum, here it is. And conservation of what? Of energy. But, and here, this is another important point. You see, now the shock, the fluid, I'm considering the shocked fluid. So the crossing of the shock has already happened. And if you remember what I stressed last time, it means that now, okay, by crossing the shock, the fluid undergoes a discontinuity, a jump, a positive jump in entropy. But after that, as long as we consider it an ideal fluid, and as long as we neglect heat conduction, viscosity, and radiative losses, as long as we do that, this is an assumption we are making here, as long as this holds, it means that entropy is conserved. And so that's why you see, and it's equivalent to applying to demanding conservation of energy. So you see here, I'm demanding conservation of entropy. But since now, for the very reasons that I just told you, this is indeed equivalent to demanding conservation of energy. Now we are exploiting what I was telling you a couple of classes ago, and what we could not write across the shock. This is not true across the shock. But after you move away from the shock, and you're considering the ideal fluid under the assumption that I just reminded you, this is equivalent. And the advantage is that you know very well what entropy, this is entropy per unit mass. So entropy looks like in the case of an ideal gas. You remember that the equation describing a reversible adiabatic is P times V to the gamma constant, which is equivalent as to say P over gamma over rho to the gamma constant. So that means that the entropy is just a function of like this, plus an arbitrary, the usual, the ordinary arbitrary constant that you have when you define a function like entropy. So you can exploit this function here and just work this out. You see that pressure, density, and velocity are all function of just this single variable, psi. Psi includes both the radius, the spatial and temporal dependence, because you have both in them. But as a matter of fact, from the point of view, from the mathematical point of view, these are all partial differential equations. But essentially, they become just partial differential equation because you have just one single variable, essentially. So the nature of self-similar solution, of self-similar equation, turns into the fact that instead of managing separately the space and time component, you just have one single variable, psi, which already encodes a given combination of space and time, which is the only possible. So you see, it's just a matter of applying or rewriting these equations. We are in the case of spherical symmetry, so it's convenient to use it for the divergence, the spherical coordinates. So this is the only, as I said, the only thing that comes into play is the radius. Of course, this then turns into an equations which depend on psi, because r gets through psi. And here I just exploited the third one, so the conservation of energy, or equivalently of entropy in this case. I just exploit this formula here. So this is what I have. I spare you the mathematical details and pains of getting through this. I immediately give you the solutions, and I show you the numerical solutions. In the case of, for example, you see that there is still the dependence on the adiabatic index, so it depends on what kind of gas you are having in mind. So let's consider the simplest case of a monatomic gas. For example, you have all hydrogen, so gamma is 5/3. You see, we still don't know beta. Beta is the coefficient which sets which comes into play here, in particular in defining also the radius of the shock. But you see, once you have the solutions of the mathematical solutions with P, rho, and V, which also will depend on beta, assuming that you know the total energy, you can determine beta by demanding, by imposing that what? The total energy of the fluid within the variable has to be E, capital E. So what is this? Integral is nothing but just what I said. In particular, what is the total energy? Well, first of all, you have to integrate all the energy released by the explosion, and which is taken by the shock fluid, of course. So you first of all, you have to integrate between 0, the site of the explosion site, and the shock radius. That's where the shock fluid lies. And then you have to integrate what? The energy density times the volume element, which is 4 pi r squared dr, volume element, integrated within the entire variable. And what's the energy density? Well, the energy density is mass density times what? Well, the kinetic energy of the fluid. The shocked fluid is moving, is expanding. So that takes energy. In particular, rho v squared over 2 is the kinetic energy of the shock fluid. But mind, part of the energy is also became internal energy, because you now the fluid is hot, the shock fluid is hot. So you also have to include the internal energy. And if you remember the formula, what we called epsilon, so internal energy per unit mass is P over rho over gamma minus 1. This is energy per unit mass, so you have to multiply in order to have energy per unit volume times rho. And you see, let's assume you know already the solution. The solution, P is a function of space and time, as well as rho, as well as V. So all these quantities depend on beta. So by demanding that all this integral has to be E, which is the initial parameter, which is the independent variable, you define the energy that you release in your explosion. And as a consequence, all this is given. You see that this turns into a condition on beta. And the numerical solution is beta in the case of, which depends on gamma. You change gamma, as a consequence, change beta. So beta is, for the monatomic gases, of the order of 2, more or less. So this is to let you understand how one can determine beta. So it's a kind of nasty calculations. It takes a while, but it's just mathematics. What I would like it to be crystal clear is the line of reasoning. So the physics that one exploits to get to the point of the solutions. I show you the plot of the solution. So this graph is the so these solutions are called Sedov-Taylor self-similar solution. So you see here the three functions that I'm going to comment are the velocity, pressure, density in relative units. So all these three quantities are in units of the corresponding quantity with 2. What is 2? Well, 2 is just reminiscent of a Rankine-Hugoniot solutions. It means all these three variables are given in unit of the same value that you have of the value of the same quantity that you have right behind the shock. And if you look at the independent variable here on the horizontal axis, is the distance from the explosion as a function of, here it's R0. R0 in our notation is capital RS. So is the shock radius. So it means that when you want to calculate the corresponding variables right behind the shock, it means that you are 1. This ratio is essentially 1. So here you are right behind the shock. And it's not by chance that all these three functions are 1, because they are the values with respect to the value that you have right behind the shock. So if you get right behind the shock, of course, V will be equal to V2, P will be equal to P1, and so on. So you see that you can use this solution at any time, provided that you scale the radius with respect to the shock radius. That's why it's self-similar. Now, this plot should make you clearer the meaning of self-similar, because you see, this solution doesn't refer to a specific time. This holds for any time. If you consider a later time, well, it means that the shock radius will have got larger, but then in the ratio, this ratio is the same. So that's the nature of self-similarity of the solution. Because if you keep analyzing the pressure, for example, when you are at a distance from the explosion, which is half the value of the shock radius at any time, well, the pressure will have the same value at any time as measured relative to the pressure behind the shock. Of course, if you imagine you ride the shock as time passes, of course, the energy that you have released in the explosion is distributed over an increasingly larger amount of fluid. So as a matter of fact, the shock will just slow down. And we know, because if you remember, indeed the velocity is decreasing, is just is a function of, you remember, the shock radius is increases as t to the 2/5. So it's the velocity is just decreasing with time, which makes sense if you want energy to be conserved. But you see, let's see exactly what the peculiarities of the solution is. Well, first of all, you see that when you are far away from the shock, still within the shock fluid, but far away, so in this region here, you see that, well, first of all, the density is very low. So it means that this shock, the effect of this shock has been that of just emptying the internal region. You have a very low density with respect to the density you have here. So it means that if you consider if you integrate, for example, the density, of course, 4 pi r squared, so you calculate the total mass, you see that just from this profile, essentially the effect of the shock is just to push most of the matter very close to the shock. You see that you have most of the matter close to the shock. This is one of the results of the shock. So you can, instead of looking at of considering a sphere with more or less uniform density, nothing like that. No, you can. It's a more realistic picture if you think of that as a kind of shell. A shell is something which has most of its mass just close to the external boundary, and that's indeed what this density profile is telling you. Most of the mass is here, is close to the shock. So it works like a shell rather than a sphere. What about pressure? Well, pressure, you see, it's not negligible at the site of the explosion, but it's constant, and it's well below the pressure that you have right behind the shock. And then again, it just goes up in a very fast way when you approach the shock. And the velocity, instead, the velocity is more kind of regular. If you work out numerically, again, you will find that most of the mass right in 1/10 of the shock radius. That's why I was telling you, as a shell, is a kind of relatively thin shell, which takes most of the shocked gas. So, and you can only prove that if you go through the set of Taylor solution. Very beautiful. There's a way to show this in picture. For example, this is the radius of the shock, in which you see, this is a two-dimensional plot, in which you see it's a color-coded plot. So the color which you see here, the scale, is the pressure. So the redder and the higher the pressure. So you see here the pressure is rather low, but then it goes up dramatically as soon as you approach the shock. Still in the shocked region, in the shocked fluid region, of course. And the density is even more extreme. The density has this profile even more extreme, because density is essentially almost negligible here, and then just gets very, very high close. That's why you can see, if you look at just at this figure, even a kid would say, oh, this is a shell, this is not a sphere. Yes, indeed. And as time goes by, you see that this is increasing, because the shock is expanding, of course, but the same profile is kept. The same profile. But what you should also notice is that the absolute value of pressure right behind the shock is decreasing. So the profile is the same, but the absolute value are scaling down. And this makes sense, because as time goes by, if you, again, imagine you are riding the shock. Of course, as time goes by, you are shocking an increasingly amount of matter. So energy is distributed over an increasingly amount of matter. So inevitably, the kinetic energy of the shock and also the internal energy of the shock, so pressure density, will decrease as a consequence. So if you see here, the top values, the highest value are in this generic, let's neglect what kind of unit. Let's consider whatever you might think of 5 here. But then here you see that the highest value is just 0.8. So indeed, the self-similar solution tells you that the shape, the mathematical shape of the profile is the same at any time, but the absolute value, so the value that you have for all the quantities right behind the shock, of course, are decreasing, as well as the velocity of the fluid. This, what we've just seen, holds as long as we have in mind the assumption. You have to keep in mind all the time the assumption that we made to use this. What are the assumptions? Well, is that the fluid is behaving like an ideal fluid, so no heat dissipation through, in particular, through radiative losses. The set of Taylor solution holds as long as we can neglect radiative losses. Oh, by the way, the assumption of cold gas at the beginning of cold fluid is that the internal energy that the fluid has prior to being shocked is negligible to the internal energy that the fluid will have after the shock. So that's what cold means. Of course, if the fluid is hot already, it means that the internal energy, so the increasing temperature that will be the consequence of the shock, will add up to something which is not negligible. So this is something different. So that's why cold. Cold with respect to what? Now you know. With respect to the energies, to the internal energy, so to the temperature increase that is caused by the shock. As I said, yes, I was telling about the assumption. We assume that the radiative losses are negligible. But think for a moment, for example, because the opacity is too large. So this same comment I was making last class. When the medium is too optically thick, well, radiation cannot escape. And also another assumption that another consequence that I made is that when we apply these conditions, of course, in principle, if there is radiation in the fluid, also radiation could in principle contribute to internal energy and pressure. But again, we are assuming that the contribution of energy of a radiation to pressure and density is negligible. And you know this is the case when these are not too high, because of course the dependence of energy density and pressure on temperature for radiation, T to the fourth. So as long as temperature is not too large, you can neglect. So that's why if you think when we applied all the equations about fluid, we neglected the possible contribution, for example, to pressure due to radiation. So you have to pay attention that when this is no more the case, this changes also. But if you imagine, so the shock which keeps expanding, at some point, so the shocked fluid just cools down and expands. So it means that at some point, you should expect that what made the optical depth too large now will decrease. So what this means? Well, you immediately see that at some point you are likely to expect that you can no more neglect radiative losses. At some point, the gas will lose with exchange heat through radiation, because at some point the fluid itself will be no more capable of absorbing radiation. So the adiabatic assumption will not hold anymore. Okay. In that case, what happens? Well, energy is no more conserved. Of course, you have energy which is just carried away by radiation. So the solution, the set of Taylor solution, cannot be more applied because energy conservation is no more valid. But what still is valid is that linear momentum. So you can, and this phase is called the snowplow phase. For the reason I comment in a moment. The snowplow in Italian is spazzaneve. So in this case, you can play the same game we played when we studied the temporal dependence of the temporal evolution of the shock radius by imposing now that the fixed quantity is no more the total energy, but is the total momentum, radial momentum component. So you play the very same game, and you end up with different coefficient, which is these guys here. And so in that case, when the set of Taylor solution is such that now radiative losses cannot be neglected anymore, so set of Taylor solution cannot be used anymore, energy is no more conserved due to radiative losses, but you are in the so-called snowplow phase, and you see that the temporal dependence on the shock radius change. Why it is called snowplow phase for what is written here? Because if you study the analog profile that I showed you and I commented in the previous figure, so the profile of density, for example, if you do the same in the snowplow phase, you see that it's even more concentration of mass close to the shock. So even more so, it's even more as I told you. And so if you imagine this, it looks like what you have about snow when you use a snowplow. So a snowplow is just pushing, it's just sweeping up all the snow. So in the end, you have something that is almost empty, all the path traveled by the snowplow, except for a big amount of snow just in front of it. Snowplow. Just a linguist, just a linguistic comment, I don't know. But snowplow, you might find also instead of U, G, H as O, W. This is UK notation. Snowplow with O, W is just American notation. So this is just. Let's see now a beautiful application I was mentioning. Well, the beauty of this is the physics, of course, not the tragic use that man has made of it. Let's see. So this is the first snapshots. These are the real snapshots of the very first atomic bomb explosion that took place in the New Mexico desert in 1945. So you see, you have the time from the explosion, and you see the fireball. So here is the scale. I strongly advise you to carry out this very simple, this very amusing exercise. You have the scale, you can measure, so this is 100 meter. You measure the size of the, these are milliseconds. You measure the size of the explosion as a function of time. Now here the energy release was huge. Now if you work out the function, something that also 12-year-old boy can do that. If you plot, if you study how the shock radius depends on time, you see that it is described by this power law with the index 0.4. This is time in milliseconds, because here milliseconds, and this is just meter, or equivalently in this way. And this holds only for the first 100 milliseconds. Now, if you remember set of Taylor solution, T is to 2 over 5. 2 over 5 is exactly 0.4, 0.4. So you touch with your hands that this is indeed set of Taylor evolution. It's the radius, the shock radius of temporal evolution that you would expect in the case of set of Taylor. And you see, if you work out also the velocity, you see that the velocity, or better, the corresponding Mach number, capital M, is much larger than 1. Indeed, this is a shock wave. This is a supersonic explosion. And what happens at 100 milliseconds? When you see that at some point the Mach number gets comparable with 1. So it means that the shock is no more a shock. And so that's, of course, the set of Taylor solution is no more valid. Why the names? Because the two guys, Taylor, the British Taylor, and former Soviet Union Sadov, within a few years, they independently calculated the total energy of this. And just looking at this figure here, this is the beauty of the physics, and that's what we are going to do now. Just once you measure, this is the function that you measure. So the ratio, the evolution of the radius is a function of time. You see, okay, this is the exactly temporal evolution of this solution of a strong shock caused by an explosion within a uniform medium, which is here the atmosphere. Well, you have to know the kind of gas air is. You can consider it, we made this many times in your previous courses, gas. You can look at air as a biatomic gas. So the adiabatic index is 7/5 or 1.4. If you get back to the set of Taylor solution and you determine beta as a function of gamma, in that case was about 2. In this case, for a biatomic gas is a little more than 1.023. You use the density of the air, and 1.22 kilograms per cubic meter. So you see, okay, let's have a look at the solution, set of Taylor solution in the case of, I know beta, I know raw density of the air. What I do not know is the energy of the explosion, E. But I know R as a function of time. So in particular, if I express the total energy, which is the only unknown variable I have here. In particular, you see that here energy depends on these two quantities, which are constant, and depends on the ratio between the shock radius to the 5th over time square. But this is something that you can estimate from here. If you work out this ratio here, you had a constant value, which is exactly, if you just plot this function point in a graph, you see that this is a power law. So if you make a log-log plot, you see that you have a straight line. So this ratio is just the angular coefficient of a straight line, something really that even a 12-year-old boy can do that. So if you do this, you see that immediately estimate the total energy. That's what Taylor and Sadov did. Of course, before they solved all the fluid dynamics, and they found the solution that carries their names. Of course, that was the most difficult part. But then after they got that, it was just a matter of applying this very easy formula. And so if you do this exercise in this very case, you end up with this value here. 7 to 10 to 13 joule. And if you remember that when you are dealing with such energetic explosions, the common measure unit is a kiloton or a megaton, depends, where 1 ton is 1 ton of TNT, the chemical explosive, and 1 ton of TNT releases an amount of energy which is 4 10 to 9 joule. So you immediately see that something close to 10 to the 14 is something close to of the order of 20 kiloton. And so that's the value they've come up with. And that's what was a secret at the time, of course. It was a US military secret. And the Los Alamos scientists estimated an energy release in, so the people who, of course, built up this weapon estimated an energy of 18 to 20 kilotons. So you see the power of this physics. Fantastic. And just for your knowledge, so this was the energy released by the very first atomic bomb that was built up. And afterwards, people were so clever, a little bit ironical, of course, to build weapons as energetic as 60 megatons. So you immediately see the evolution of this crazy things. And but apparently also current arsenals are essentially consist of much less energetic bombs, just because they're thought to be less devastating, less the bombs of about 1 megaton are considered to be more destructive, more effective. So apart from the scary aspect, historical and whatever aspect you might consider, just focusing on the physics, which is what in this context we should care of. So this is really, really, so that's why you see, it's not by chance that people got interested in this kind of phenomena, just because, of course, they wanted to describe the physics that is ruling this kind of explosion. So strong shocks. And you see incredibly how beautifully the Taylor solution here apply. It's interesting to calculate, to exploit all the solutions, to find also, here we just derive the total energy as a function of the radius. But let's see also, what about pressure, velocity, temperature? It's very interesting. So what is the post-shock density? So the density that it lies here, for example, like close to the shock. So we are in the case of an adiabatic shock. So again, so you immediately see that here again in the first 100 milliseconds. So radius velocities are negligible. The fireball is too thick. So you see that density, if you remember, density that doesn't really diverge. There's this factor which depends on gamma, and gamma is 7 over 5, so about 6 times. So here density just right close to the shock is just 6 times more or less more dense than the normal our air density in normal situations. The mean molecular weight is about 10, considering the composition of air. What about the shock speed? Well, just calculate from you can calculate it straight away from the figure, is of the order of, at least within the first milliseconds, is of the order you see of kind of 15 kilometer per second. If you think that the sound speed is 300 meter per second, it means a kind of factor of 50. So the Mach number was at the beginning a factor of 50. You realize what supersonic means in this case. And what about the pressure? Well, again, 2 over gamma plus 1 raw shock velocity. So you see that the pressure was really huge. It just close at 1 millisecond was kind of 2,000 atmospheres. So really, really. So what about temperature? Well, you can exploit, pressure, density. You can exploit the equation of state. that we saw many times. So you can do this way. Just I inverted just the equation of state. What we know here is just use density 6 times the air density. And what else? Here is K, the Boltzmann constant. If you multiply by the Avogadro's number up and down, here you have Avogadro's number time hydrogen mass, so 1 gram. So 10 to minus 3 gram. R is not the radius. R is just the universal constant of gases. So 8.31 joule per Kelvin per mole. So you end up with a temperature which in the first milliseconds was several thousand degrees, several tens thousand degrees. So you see the beauty of this solution. It tells you exactly. It allows you to estimate all this, and so you also see that the temperature here is incredibly large, as expected, as one should expect. So again, all this energy, you see, this energy released this tremendous release of energy release. Part of this energy goes into kinetic energy because the fluid, it's expanding, and you see what kind of velocity. But also part of the energy goes into internal energy, so to make the air hot, terribly hot, I would say. And okay, and so this is also explaining you why there is also the terrible historical account about you have a fireball that hot, so also the radiation just coming from the surface of this fireball is also, as a consequence, very, very powerful. Okay, that. Okay, I think we still have some time. I wanted to make a comment, but all of a sudden I must have forgotten. Anyway, it means that it's not very important. Okay, moving on. Oh yes, that's that's a curiosity I wanted to say. There's a book about that one of the leading scientists who led these experiments was Enrico Fermi. He's legendary for many things, but one of the things is that was capable of estimating the so-called Fermi problems. He was able to estimate many things that in a very simple way, apparently, because he is one of the physicists who was able to immediately understand the essence, the dominant effect that was giving you whatever. So in this case, his capability was legendary because he just took a piece of paper, he just broke it into many pieces, just tore it up into many pieces, and just by looking at the way these pieces of paper were just following down as a consequence of the wind produced by the explosion, he was able to estimate the total energy. And it just went, of course, very close to the volume. So this is a nice account, a very amusing account also that gives you the measure of of physicists like Enrico Fermi. So that's a curiosity. So far, we consider the hydrodynamics of Newtonian fluids. When the quantities you are dealing with are non-relativistic, so velocities are non-relativistic and whatsoever. What happens when you move instead to a relativity context? Well, in that case, you have to consider relativistic hydrodynamics. So we introduce this, and then we will explore more in detail on Monday. But essentially, what changes here? So we have to start from scratch, in a sense, because all the three equations that we've seen, we have to express them in a new light, taking into account relativistic dynamics. And in particular, as well as when we were considering particles, you know that when you move from Newtonian physics to to special relativity, you do not have two separate objects for one particle describing the energy of one particle and the linear momentum. You have just one single object, which is the four energy momentum momentum quantity. In the very same way, when you have in mind a fluid is something for which you think of energy and linear momentum per unit volume, so energy density and linear momentum density. And if you think for a moment, what we've ended up with at the time was on one side conservation of energy, and on the other side conservation of linear momentum, Euler equation. And when we obtain Euler equation, we end up with an object which was the stress tensor, if you remember. We were in the Euclidean space, 3D, and the stress tensor was telling us the content of linear momentum density. And so given that linear momentum is a vector, and so the flux of linear momentum, the flux means that you have to consider all the possible direction in which the linear momentum is propagating, but since the linear momentum is itself a vector, you need a rank 2 tensor, which was indeed what we had come up with. Now, energy and momentum, as you can imagine, get together. And we have the relativistic analog of the stress tensor, which is called stress energy tensor, which is a rank 2 4 tensor, of course, because space and time, space-like and time-like components now get together. Let's see the meaning, and we call it capital T. So it's a rank 2 tensor, and this the one you see here is expressed in a one special reference frame, which is the reference frame in which the fluid is overall at rest. And we will see why there are these numbers. But let's first, prior to doing that, let's see the content, the meaning of the stress energy tensor. Well, you see that the time-like component 0, 0, the diagonal, is what? Well, is density of what? Of the time-like component. But the time-like component is energy. So T00 is density of internal energy. You can think of the meaning of a generic component as when it is the time-like component, so 0, it is density or flux. And the second component tells you the flux along which component. But in relativity, the flux along the temporal component, is density. Flux along temporal is density in relativity. So here you have the flux of energy, flux along the temporal component, so density. So density of energy. Let's consider the mixed component. So one index is time-like, 0, and the other index is spatial, I. In this case, you have two different interpretations. Well, if you consider I is relative to the momentum, so it's momentum flux of the IF component, flux along the 0th component, so along time, but flux along time is density. So this is density of the momentum. Of course, the momentum is a vector, so I is just the IF component. 1, 2, 3, which means X, Y, Z. But you see, you can also give the other interpretation. You can think of 0 as the energy. So energy flux with respect to the IF direction. So this can be if I is 1 or X, this means energy flux along X. And then the energy flux is a vector, is a 3D, is a spatial vector. And Tij is indeed the stress energy tensor that we already knew from the Newtonian physics. So is the flux of linear momentum component I along jth direction. So, and here I put it in the same way. But when I say along a jth direction, it means that if you multiply by daj, it's the total amount of linear momentum along I crossing a surface daj. The meaning is the same. So you see that you have a generalization of the stress and of the stress tensor that we saw in Newtonian physics. This is the guy. He should be the equivalent, more or less, of the spatial component. But here you have all, which is included. You have energy density, energy flux, and momentum densities. So it's a more complex and more complete object, which works as a as a rank 2 four tensor. So it transforms when you move from one reference frame to another inertial reference frame. You go through Lorentz transformation in the very same way that we learned at the beginning of this course. And in this very case here, E is energy density and P is pressure. In what reference frame? Well, in the reference frame in which the fluid is at rest. Because you see that you have just, in particular here, you have no energy flux. The fluid is not moving, and also no, apart from the pressure component, also for the momentum. In a generic inertial reference frame, so no more necessarily the frame in which the fluid is at rest. So when you have to move from this guy here to another reference frame, well, you have to apply Lorentz transformation. And in particular, let's consider again the easiest possible case. If you have in mind the way we defined the Newtonian stress tensor using the combination of two velocities and the metric tensor, here is exactly the same generalization. You see, where capital U is the four vector, which describes the velocity in the Eulerian context is the velocity of the fluid at some point. In this case, of the velocity of the reference frame, of the moving reference frame you are considering. So you see, if you remember, this is a generalization of this case, because if you remember, let's consider the obvious case in which you are indeed in the rest frame of the fluid. Well, gamma, it means that gamma is 1 and beta is 0. So this guy is 1, 0, 0, 0. And indeed, if U0 is 1 and U1, 2, 3 is 0, you immediately see that this guy here takes this form here. But this is a four tensor. There's no way you can immediately see. This is written as, you immediately see that this guy transforms as a rank 2 contravariant tensor. There's no way. And in particular, if this guy is in the reference frame in the moving frame of the fluid, as this guy here, this is its generalization. So in particular, okay, this is just written in a geometric way, so coordinate independent. So it's interesting, and this is the very last thing for today. If you rewrite the stress energy tensor in a reference frame which is moving with a boost along the x-axis with respect to the co-moving frame, it's something for kids to derive the new look. So in particular, all the components of the stress energy tensor in this very frame. Well, if you are as I said, if you consider a frame which is moving along x, the two components of the four velocity will be gamma, this time-like component, and the only space-like component which is non-zero is of course the one along the direction of motion, so the x component, which is gamma beta here. So you see, it's just something for kids to see that from here, just exploiting this guy. And I strongly advise you, do this. I remind you here, the metric tensor that I'm using, this is the flat space-time, so Minkowski metric tensor, so 1 and -1 for the spatial components. Diagonal, of course. I strongly invite you to prove that from here, In the case of a boost along the x-axis with this forward velocity, from here you get here. So this is the stress energy tensor of the fluid in the moving frame. Sorry, not in the moving frame, in a frame in which the fluid has this forward velocity. Okay. Of course, if you consider a more generic boost, so not necessarily along the x-axis, also y and z component get mixed, and so you have that correspondingly. This is all for today. It's a very dense class. You have several days to think about. I strongly advise you to review what we've gone through, and we will next week we will be dealing with the analog development in terms of relativistic now hydrodynamics, and we will see essentially that apart from all the changes that one gets when moving from Newtonian to relativistic physics, you'll see that big change also will be about conservation of mass, which doesn't hold anymore in relativity. But this is another story I will tell you about next week. So, any questions?